In the last lecture, I was starting to talk about some kind of basic review stuff about C++. I'm not going to go into like a lot of detail about things. I'm just going to focus on a few very kind of strategically chosen things that are issues in my experience that students sometimes have problems with. So const was one of the things that I identified. So I'm going to spend a fair amount of time talking about const and also a bit about constexpr as well. And also some other things, kind of random things here and there that sometimes trip students up. So in the last lecture, we're starting to talk about const. And when we're dealing with non-reference, non-pointer, non-iterator types, typically const doesn't cause any problems. This is just kind of summarizing a little bit from the last lecture. If we have an integer variable I, which we initialize to 0 when we define it, we can of course say I equal to 42. There's no problem because I is not a constant variable. We're allowed to change it. But if we create a variable ci, which is an integer that's constant, and then we try to assign a value to it after it's been created, we can't do this. We get a compile error. But this typically doesn't cause problems for people. I mean, what causes problems is typically when there's reference types or pointer types or iterator types that are involved. And this is really what I want to focus on primarily. So again, there's some of these slides. So there's more examples on the slides than what I have time for. So some of the slides I skip over. If you're finding some difficulty with some of the things I'm talking about, you might want to look at some of the additional examples. Anyway, so I'm going to start out by talking about the const, qualifier, and pointer types. So what's special about pointer, iterator, and reference type is their whole reason to exist is to refer to another object. The pointer points to another object. So what we have is a picture, for example, that looks something like what's shown here. Memory is essentially a big linear array of bytes. And we have a pointer, and the value of a pointer is just an address in memory. So for example, maybe we have an integer, an int, which is called I, which resides at memory location 2000, and we initialize our pointer p to point to I. All that's going to do is it will store the value 2000 as the value of the pointer, and when we dereference the pointer saying star p, what that does is it goes to memory location 1000, where the pointer is stored. It reads the value, it goes 2000, that's where we need to go. Then we go to 2000 and we read the value, so star p will give you 42. This is called dereferencing the pointer. So there's always two objects that are associated with the pointers. There's the pointer itself and its value, which we can change or not change depending on whether that thing is indicated as being const. And then we have the pointee, the thing the pointer points to, which we may or may not be able to change depending on whether the pointee is const or not. And again, the way to think about const is it's essentially sort of like a contract in the code. Some part of the code is promising to another part of the code that even though otherwise it would have the power to change something, it's forgoing that power and saying, I promise I will not change this particular entity. So this is the best way, I think, to think about const. Because the pointer and pointee are separate objects, their constness can be controlled independently. So for example, I have this integer variable I, 42, which is initialized to 42, which is this I here. And then I can create a pointer called p, and there's kind of 4 different variations of constness that I could have for this pointer that I create. And pointer types in C and C++ read from right to left. So the star is read as like a pointer. So reading from right to left, this is a pointer to an int. Reading from left to or right to left here, this is a pointer to an integer that's constant. Reading from right to left here, this is a constant pointer to an integer. And then reading right to left here, this is a constant pointer to a constant integer. So if we look at these, in the first case, this pointer is we're allowed to change the pointer value itself, and we're also allowed to change the thing it points to, because neither one of these things have been flagged as being const. In the second case here, we have a pointer to an integer that's constant. In this case, the pointer itself can be changed. We can make the pointer point wherever we like, but we can't change the pointee, because the pointee has been flagged as const. It points to a constant integer, an integer that we are not allowed to change. In the third case here, we have a constant pointer to an integer. This would correspond to the case where we're not allowed to change the value of the pointer. So this 2000 is stuck there forever. We can't change it, but we can change the thing it points to. We can dereference the pointer and change what's at memory location 2000 where it points to. And then in the last case, we have a constant pointer to a constant integer. In this case, we can't change the pointer. It's stuck pointing wherever it's pointing until the end of time, and we can't change what it points to either. And which of these you want to use will depend on what goal you're trying to achieve. But generally what you tend to do is, like, if you know you don't need to change something, you make it const. So if you know you don't need to change the pointee, make it a pointer to something that's const. If you know you don't need to change the pointer, then you might as well make it const. Although typically the pointee is the one that causes more problems. When you get the constants of that wrong, and typically what happens is you forget to put const on something where it should be. Anyway. Any questions about this before I go on? Okay, I'm going to skip over this slide. Now let's focus on reference types. So reference types are also kind of similar in nature as pointer types, as I kind of alluded to before. Their whole point of existence is to refer to some other object. So then there's the issue of, is the reference itself something you can change? And can you change the referee, the thing the reference refers to? In principle, these things are completely separate from one another, and you could independently change whether the reference is const or not versus whether the referee, the thing that the reference refers to, is const or not. However, as we discussed before, in C++, you can't rebind references. So what I mean by this is once you initialize a reference, it will refer to that thing until the end of its lifetime. There's no way to say, no, I want to do over, I want this reference now to refer to this other thing. Because you can't do this, essentially references are always constant in the language. The reference itself is always constant in the sense that you can't rebind it and make it refer to something else. So for this reason, the language is defined in such a way that it says you can't even attach any const qualifier to the reference itself. It's just const. No matter what you put there, it's const. And you can't even say it's const. It's just built into the language. But in principle, you can think of it as being there. It's helpful in terms of understanding things, I think. So when we're talking about references and whether to include a const or not, really what we're talking about is the referee, the thing that's being referred to, because the reference itself is always const. It's baked into the language. You don't even type const. It just automatically is const. So let's look at some code example below here. So I have an int variable j and k, which I initialize to some values. Then I create this is what's called an L value reference. There's two types of references in the language, which are designated by an ampersand in the case of L value references, and a double ampersand in the case of R value references. For the purposes of what I'm going to talk about here, it doesn't really make too much difference whether there are R value references or L value references. I'm just going to stick with L value references in these examples because for the most part, these are the types of references that you use most frequently, except in certain select circumstances. That's pretty much the only places where R value references tend to be used. Anyway, but whether they're L value or R value references, it makes no difference. They're just a nickname or alias for another object. It's still a reference. Anyway, so we're creating a L value reference to an integer, which is called I, and we're binding it to j. When you create a reference, it must be bound. In other words, initialized at the point where it's created. You can't have a reference that's just dangling. Anyway, so essentially after this line is hit in the code, I mean, essentially I becomes a nickname for j. If I change I change j. If I change j, I change I, because they're basically the same thing. They're reference aliases for one another. On the next line here, I create a reference to a constant integer, a reference to an integer that I'm not allowed to change. So in this case, the referee is const. I can't change the thing that's being referred to by the reference. And I'm binding the reference to j. Interestingly, I can change j because j is not, I haven't promised not to change j. There's no const out here, but I can't change j by changing ci because ci is a reference to something I'm not allowed to change. If we keep going through here, I'm trying to essentially rebind this reference. I've already said ci is a reference for j. Now I'm trying to make it like do a do-over here and say, no, I want it to be a reference for k. This is a compiler error. The language doesn't allow you to rebind references. So this is what I'm trying to illustrate by this line. Then in the last line here, we have a reference called r, which is a constant reference to an integer. This const is trying to be applied to the reference itself. But as I mentioned before, in the language, references are always constant in the sense you can't rebind them. Once you say a reference refers to something, it can't be changed. Therefore, instead of saying that you should just always put const here, the language says you don't put const there ever. You're not allowed to put const there. It's just understood that it's const. So it's implicitly always const. But I think it's helpful for understanding like issues revolving around const to understand that effectively, like when you write the code, it's as if there's a const here for every reference in your code. It's just you're not allowed to write it. It's implied. And then that will help you to remember that you can't rebind references because they're essentially always implicitly const, the reference themselves. Any questions about any of that? Okay. Then we're going to go to constexpr. So this, depending on what you were introduced to when you were first introduced to C++ and when you took that course, you may or may not have talked about constexpr. But I'm going to go into this in quite a bit of detail because we're going to be doing some fancy stuff with it. Essentially, constexpr expresses a different kind of constantness than const. Const, I think the best way to think of it is really in terms of contracts in the code. One part of the code is saying, even though I have the power to change this variable, I forgo that possibility and I promise that I won't do it. And then essentially the compiler will enforce this. Constexpr is a different notion of constant. Like literally the thing is so constant it can't change. I don't need to run the program to know what the value of the variable is. I know the value at compile time. Like a classic example would be pi. The value of mathematical constant pi, it's not ever going to change. It's it's an artifact of math. So I don't need to run a program to figure out what pi is. I know what it is. It is what it is. It's the 3.14 whatever. So constexpr, which stands for constant expression, which is basically just a fancy way of saying the thing is so constant that I know what it is at compile time. It's an expression that's constant. The compiler doesn't need to run any code to figure out what its value is. So when I'm defining variables, I can throw in this constexpr keyword. And what this is saying is that the variable that I'm declaring or defining is a constant expression. In other words, you must set the value of this variable at compile time, and it cannot be changed. So it's implicitly const. Like when you write constexpr, you're also implicitly making the promise you will never change this thing, because effectively it becomes a compile time constant, so there's no way you can change it. But it's doing more than just saying it's const. It's saying it's known at compile time. So kind of implied in this is the fact that whatever you put on the right-hand side, that you initialize this constexpr variable to, the thing on the right-hand side of the equal sign, the initializer, it better be something that you can compute at compile time, because you're telling the compiler, I want you to initialize the value of x, fix its value in stone at compile time. And I want you to fix its value to this thing on the right-hand side of the equal sign. If the thing on the right-hand side of the equal sign is something the compiler needs to run the program to figure out, well, good luck with that. It's not going to be able to it can't compile this, right? So it's really important to understand that when you make things constexpr, the consequence of this is that the thing that you're using as the initializer must be something that can be computed at compile time. Otherwise, this can't work, right? Because you're saying, choose the value of this at compile time, but I'm not going to tell you at compile time what the value is. The compiler can't do that, right? So you can't just kind of willy-nilly make everything constexpr in your program, because most things in variables in your program are not things that you know their value at compile time. But sometimes you do, and when you do know, you can sometimes save computation by forcing things to be set at compile time rather than happening at runtime. So if I look at the code example that's given down below here, I have the same variable up above. So x is initialized to 42. It's constexpr. Then I create just a regular int variable called y, initialize it to 1. And then I try to initialize or set the value of x to 0. Well, this will generate a compiler error because when I declare it x, I said it's constexpr, which implicitly makes it const. Like I'm making the promise I won't change it because I'm telling the compiler fix its value at compile time. So if it's fixed at compile time, obviously I can't change it when the program's running. So this would generate a compiler error, which is maybe not so surprising. Here I have some stuff with references and pointers. So here I'm trying to create a reference to an integer that's constant, which is called x1, and I'm trying to bind it to x, so x1 will just become a nickname for x. This is perfectly fine. Even though x can never be changed, the compiler knows that everything is good and well in the world because this is a reference to a constant integer. I cannot use this reference x1 to change the thing it refers to because I said it's a reference to something that's const. So the compiler goes, okay, even though x is a constant expr variable, it can't be changed. Everything is good because there is no way that I'm allowing you to change it because you said that this is a reference to a constant integer. And then we have sort of a similar sort of picture here on the next line, except this is the same sort of scenario but with a pointer. So here we're taking a pointer to an integer that's constant and we're initializing it to the address of x. The compiler will also be happy with this line here because this doesn't give us any backdoor way that we could change x. Because we can't change x, right? It's a compile time constant. So this is okay. The next line, though, this is where things, we start to try to do some really nefarious things in our code. So here we're creating a reference to an integer called x2, and we're trying to bind it. In other words, initialize it with the value of x. So x2 effectively becomes a nickname for x. The compiler will generate an error on this line when we're trying to compile it. The reason why is that we made an implicit promise that x won't be changed when the program is running by making it constexpr. It's a compile time constant. We can't change it when the program is running because its value is fixed at compile time. It might not even be a variable in the program. It could be encoded into the CPU and the actual instructions themselves, the opcodes and so on. So there might not be any value that you could change even if you wanted to. So the compiler is going to generate an error here. The problem is that this is a pointer to an int. So we could dereference P2, say star P2, and then we could say star P2 equals something. If this line of code compiled, we could go to where the pointer points and change its value, because the pointee is not const. So the mistake here is really this should be something like const int star. That then the pointer is pointing to something we're not allowed to change, and the compiler would be happy with this line of code. In C++, the sizes of arrays have to be constant expressions. They have to be known at compile time. So this line of code here is perfectly valid because x up above is a constexpr variable, so x is known at compile time. So this is fine because the language requires that sizes of arrays must be known to the compiler at compile time. However, if we try to do this line of code here, the only difference is that y here is not a constexpr variable, so we don't necessarily know its value at compile time. This is an error simply because, again, in the language, the C++ standard specifies that sizes of arrays must be constant expressions. Y is not a constant expression. It's not known at compile time, or not guaranteed to be known at compile time. Any questions about any of that? Okay. So const qualifiers and functions. So this is where things often can go really wrong in terms of getting your code correct with respect to const. It's sometimes referred to as const correctness. I may slip into using C++ terminology, but when people talk about const correctness, they're talking about using the const qualifier correctly. It's such a fundamentally important thing, there's this term for it, const correctness of your code. And one place where this can come to bite you is in terms of API specifications and like function declarations and so on. So this is what I'm going to talk about here. So const qualifiers, again, the way to think about const is it's for making contracts or promises between different parts of the code, where one part of the code is promising not to change the state of other parts of the code, other objects in other parts of the code. So for example, the string length function from the C+ or C standard library, this is the declaration for it here. Basically, in case you're not familiar, if you haven't used C, basically it takes a pointer to an array of characters, and then of a null terminated string, a string terminated with a 0 character at the end, and it returns the length of that string. Now, the keyword const here is extremely important. Like a common mistake for people who don't know how to use const correctly is maybe when they're writing the code, they would leave the const out. The consequence of leaving const out here, well, maybe I'll start with the fact that the const is there. The fact the const is there is saying the function strlen, string length, makes the promise that it will not change the thing that this pointer points to. In other words, the string that you're giving it to compute this length of, it promises that it will not change your string. Now, if you take away the const, it's no longer making that promise. If we were to take the const away, and this would be incorrect code, then what it's saying is, yeah, I'm happy to return you the length of the string, but by the way, I may change the value of your string to whatever I feel like. Obviously, this would be kind of a useless thing, right? The string length function would be useless if, it may change the string value, because sure, it says the length of the string is 5, but after it returns, it might not be the same string anymore, so the length could be something else. The function would be completely useless, right? But if we leave out const, that's exactly what we're saying. We're saying, hey, free game, if it's like a free-for-all, I can change that whatever is at that pointer to anything that I want. I make no guarantees. So when you're writing functions and designing APIs and so on, if you have a reference or a pointer that's being referred to and you know that you're never going to change that thing that's being referred to, you want to make sure that it's indicated as being const, because otherwise the assumption will be the reason you didn't make it const is because you plan to change it, at least in some circumstances. And the even more important thing maybe is that once you leave the const out, like the compiler enforces constness. If you say that, for example, if I did something like I write the code and I leave the const out, the compiler will then get very upset with you if you try to pass it like a pointer to a constant string to this function, because it will say, this function might change the string, but the string that you're passing is a constant string. Therefore, if I let you call this function, it might change a constant, but that's not allowed in the language, so I'm not going to let you do it. Compiler. So this is the sort of thing that the sort of way that which problems with constness often manifest themselves is you get lots of compiler errors where you're trying to do things that might seem reasonable and the compiler is saying, no, I'm not letting you do that because there's a back door whereby you could change something that's const in an indirect kind of manner. The same sort of idea applies for references here. So like, for example, here we have a function that takes like a complex number. Complex double is a template class in the standard library. So it's like a complex number, the real and imaginary parts are doubles, and it's computing the square of the complex number and then returning it back to you. But it's passing it by reference, probably because the A complex double is not a huge type, but it's maybe something on the order of like 16 bytes or 32 bytes or something like that. So it's not like super small, so it's probably more efficient to pass by reference. But we don't want the value of this argument that's being passed into the function to be changed, because the reference is going to be referring to the argument in the caller that's being passed in. So it's like a variable of the caller, and we don't want the function actually modifying our variable. So the way that the function makes it clear that it's not going to change the value of the variable is it says it's a reference to something that's const. So it's making the promise that I will not change the value of x, which is referring to some local, probably a local variable in the caller. And the compiler, the important thing is the compiler enforces this. If it sees you doing anything inside the code for square, which would involve changing the value of x either directly or indirectly, it will say compiler, you can't do this. So the compiler enforces this. Yeah, so I guess I kind of covered this when I was talking about the slide. This is just kind of a more detailed example with the string length. Maybe I'll skip that one. Maybe talk about the square example just with the reference here, just to talk about one of them in a little bit more detail. So for example, here's kind of just more detail showing the actual kind of the definition of the square function. So this is wrong because really this should be we're passing by reference, and we should be passing by a reference to something that's const, rather than just a reference to something we can change. Because in principle, although this function doesn't change the value of z, you can see this just by the code, it's one line, obviously it doesn't change the value of z, it doesn't matter. It doesn't matter what the code actually does. What matters is what promises you're making in the declaration. And this thing is not promising not to change z, so the compiler will assume this function will change z under some circumstances. You might say, well, wait a minute. I mean, hey, it can look, I'm an idiot, and I can look at this code, and I can see clearly it doesn't change z. So why can't the compiler just look at the code and say, I didn't put the constant, but come on, it doesn't change z. It's obvious, right? But the thing that's important to understand about C++ is when you're compiling code, you compile it like one translation unit at a time. So you're compiling like one C++ source code file at a time. So in order to use a function square, the only thing that needs to be visible is a declaration of the function. The compiler does not need to know what the definition of the function is for you to call it in your code. So the reason why the situation I was just describing a moment ago doesn't work, like why you can't say, well, why can't the compiler just look at it in the case of simple functions like this and say that it doesn't change the value? The reason why is that the definition of this function, in other words, like what's in between the brace brackets here, could be in another source code file, which the compiler has no idea what's in it when it's compiling this file here that we're looking at. So the problem is like the compiler can't look at the definition because in most cases it won't know what the definition is because it's in a separate file. So this is the reason why that kind of solution doesn't work. More fundamentally though, there might be some, if this function gets a lot more complicated, it might be unclear whether or not the value of z might be changed. But even in cases like this where it's trivially obvious, the problem is the definition could be in another file. The compiler can't tell when it's compiling this file whether or not that function makes changes to the parameter z, so it must assume the worst, which is that it does. Anyway, so this is the reason why things are kind of structured the way they are in the language. If you don't promise you won't change anything, the presumption is, in some circumstances at least, you are going to change it, and the compiler will take the necessary precautions under that assumption. So if we kind of look in more detail down below in the code that's actually using the above like bad code, we're calling the square function twice. I have two examples where we're calling the square function. So in the first case here, we're passing it a parameter C1, or an argument C1 is being passed into the function. C1 is a const variable because we declared it as being a constant complex number. So it's a number that we're promising we're not going to change. So C1 is something that cannot be changed because we promised we're not going to make it. And we even did this when we declared the variable. So like when this happens, the variable is never going to change because the person who created it said they're never going to change it. So kind of transitively, there's no way that this variable could be changed in valid code. But when we try to call the square function here, we're passing now a pointer, or we're passing a reference to something that's const. So what's going to happen here is the compiler is going to give you a compile error. Even though this is a perfectly reasonable thing to do, like typically these two pieces of code, this function here would be written by some library writer, and then this is maybe written by you, the application writer. And then what happens is the application writer gets really violently upset with the library writer because they're a moron because they didn't make the promise that they didn't change this parameter that's being passed by reference. The reason why this is a problem is this is a very reasonable thing to do, right? I have a constant complex number, and I just want to know what's the square of it. Why should I not be allowed to do this? But the compiler is going to step in and say you can't do this Because if I allow this code to compile, what's going to happen is this thing that's not allowed to be changed is going to be passed as by reference to this thing that is allowed to be changed, meaning that inside this function, this variable, if it changes the value of z, because z is a reference to C1, that changes the value of C1, because z is just a nickname for C1, right? So if the compiler allowed this to compile, you have a backdoor sleazy way that you could change something that's const when you're not supposed to be able to do so. Like you promised not to change it, but now you're trying to change it. So the compiler sees this and it says, no, this is invalid. You can't do this. But the problem really is the person who wrote the library made the mistake. They should have made the promise that they won't change z by putting a const in here. Then the compiler will be happy because then you're passing a reference to something that's const. It goes, okay, this could be dangerous. You're not allowed to change this. And then it looks at the reference and goes, oh, but it's a const reference. The other code's promising not to change it. It's okay. I'll let that compile. Any questions about that? Okay. And this is basically how we correct it. It's very easy to fix. We just put a const in here and then everything is good. And basically that's kind of the rule that you want to use. Like it's very easy to write code that's const correct. I mean, basically what you need to do is anytime you declare either a pointer type, reference type, or iterator type, these are basically all things that refer to another thing. So there's always the issue of, is that other thing allowed to be changed? You have to ask yourself the question, is that thing that the iterator, pointer, or reference refers to, is it something I'm allowed to change, or anything that I ever want to change ever? And if the answer is no, I never want to change it, make it const, and then everything just works. Everything will be fine. But the problem is, and it sounds so simple, right? But the problem is people who are new to the language often lack the discipline of every time they declare a variable of either pointer, reference, iterator type, they don't stop to think, well, am I going to use that pointer, iterator, or reference to change the thing it refers to? And then because of that, they don't choose const appropriately, and then basically it's kind of all downhill from there. So as long as you follow that basic rule, then you'll be fine. But you're probably even thinking, well, I'm not going to do that. But statistically speaking, you will. Because if I ask a question like this on the final exam, for example, my experience is like 90% of the class does it wrong. So anyway. I mean, it's based on only the statistics of teaching this course one time previously, but still, it was a large, as large a class as this, so it's a statistically relevant size number of students. So before you start thinking, no, I wouldn't do that, be careful. I'm sure some people wouldn't, but there's a lot of people who might think they wouldn't, but they will. So be very careful about that. Let's see, what did I want to talk about here? Oh, some other things about const as well. So here I have some very simple predicates, is even and is odd. By predicate, I just mean a function that's testing like one of a small number of cases, like it's checking to see, for example, whether a number is even or odd, an integer is even or odd, and then returns true or false. This is a declaration of is even, and basically what we're doing here is we're putting a const in front of the unsigned int. So basically we're passing an unsigned integer type into this function and it returns true or false, whether the integer is even or odd. Not a very exciting function, probably just one line of code. But this const here doesn't really make sense if you stop and think about it. This is kind of a more benign abuse of const in the sense that a compiler, I don't know any compiler that will actually complain about this. Like technically it's invalid code because you shouldn't const qualify something like this. You shouldn't be putting const in front of this for reasons I'll explain in a moment. But I don't know any compiler that actually complains about it. You might get a warning just saying, what are you doing? Or actually some compilers, maybe a lot of compilers would just ignore it altogether. They just say, you wrote const, but yeah, I'm going to ignore it. It doesn't make any sense. The reason why it doesn't really make any sense is like, what would this const be referring to? Like when the purpose of a function declaration, and by this I mean a declaration that's not a definition. So this does not include the code for the function. It's just a declaration that like not a definition. So it's a declaration that doesn't include the code for the actual function. That follows down below. The purpose of a declaration is just to say what's the interface for the function, essentially, right? So the person who's calling it can make sure that they adhere to the interface. If you think about what this const would refer to if the compiler weren't to ignore it, well, you're passing this value by value because there's not any reference or pointer here, right? So the integer that's being passed into the function is being passed by value, right? So if I say that you can't change this value, where does this value live? It's a local variable of a function, right? It's a local variable of the function you're calling. So when you put a const in here, what you're trying to say is, me as the user of the library, I'm dictating down to you, I don't want you inside your function changing this local variable. It's kind of ridiculous, right? It doesn't make any sense, which is the reason why the language just, the compiler will ignore you if you do this effectively. It doesn't really make any sense. This is not like a reference parameter or pointer. If you're talking about references and pointers, then of course const can make a lot of sense for the thing that the reference or pointer refers to. But here what we're talking about is the actual thing that's being passed by value, whether or not it's const. And the thing that's passed by value is essentially like it's a local variable of the function. So you're kind of trying to dictate something about the implementation by writing this in principle, which doesn't make sense. Anyway, it's less of a problem if you put it there in the sense, again, the compiler, any compiler I've ever seen will just ignore it, but technically it's kind of wrong. In the case where we have the definition, so this is like a declaration that's not a definition, so it doesn't have the actual implementation. Here we have the actual definition. So a definition is a declaration plus the actual code that implements the function. In this case, though, it might make a great deal of sense to put const here, because now we're providing the implementation. So if I put const here, what I'm saying is that inside this function, I promise not to change x. But up here, it's kind of ridiculous to put const, because you're saying inside the function, I won't change this thing that doesn't even have a name anyway. Because there is no name, because in declarations you don't need to give the names of variables because they're irrelevant anyway. They're not really part of the interface. So anyway, that's kind of the deal there in terms of like why const doesn't make sense here, and the compiler will essentially just ignore you. Whereas here it might make sense. You might not put const here. If you don't put const here, it just means inside the function you could change x if you wanted to. But some people might write a const there just to be kind of extra careful if the code was a little bit longer, just to prevent against typos where you accidentally change x but didn't mean to. And I think that's really all I want to say about this slide. And by the way, these notes that appear on some of the slides, if you click on them, they just actually link to the C++ standard. I don't recommend really, this is really more for helping me when I want to look up some of the finer points. Sometimes I put links to the standard so that I can quickly look things up and not have to remember where they are, because the standard, if you've ever looked at it, and if you did, you probably wish you didn't. It's like a few thousand, last time I looked, it's about maybe 1,500 pages, and it just grew by a huge amount for the C++ 20 standard draft. I think they're probably over 2,000 pages probably by now. It's getting really out of control. So finding things is kind of difficult. Anyway, you might want to follow a few of these links and just go, oh my God, I can't read this stuff. What are they talking about? It's like another language. You don't want to try to learn a language by reading the standard. It's written for experts, and it's written like a legal contract. If you've ever read any legal contracts, it's like you probably just went, oh my God, I'm paying for a lawyer because I can't understand any of this. Same thing here. Anyway, but I have the links in there mainly for me, or maybe some people who are like really advanced who just want to go and look at the actual relevant parts of the standard. But I don't really intend you to use it in this course, except maybe to look at it and go, nah, I don't want to do that anymore. I'll just trust what the instructor says that it's correct or close enough that it's not worth my time to look at the standard. With that said, I have a bunch of code examples that I want to go through. Some of them relate to const, some of them relate to some other kind of things that often trip students up. So I just thought I'd mention them sort of at the beginning of near the beginning of the course to try to save you some headaches a little bit later. So the first example, and by the way, maybe in the questions I'm about to ask, like don't look at the next slide because the next slide has the answer to what I'm asking. So if you look at it, then it kind of defeats the purpose. But can anyone see anything wrong with this code, in particular with respect to constants? There's a lot of problems in terms of const, and it's kind of being not used correctly. Again, looking at this without looking at the next slide, because essentially it has answers to what's wrong here. Again, the issues are all kind of revolving around const, so you can kind of limit your looking at the code to things that pertain to constants of various quantities. Anyone want to take? Yep.
Should the first square function be constant, since it's not expected to change the value of x? Okay,
there's a const missing, but where should the const go to be more specific? Pardon me?
I'm not sure.
Oh, okay. Okay, well, you're right. There should be a const. Yeah?
In front of state complex?
Yeah, I mean, essentially what we want to do, because this code here, you're passing by reference, but clearly the intention is not for this function to change the value of what that reference is referring to. So we want to make the promise that we're not going to change it explicit by putting a const in front. So then if we put a const here, and then what we're going to have, references, pointers read from right to left. So it's a reference to a constant complex number long double. So if we do that, we add a const in here, then basically the compiler would know that we're never going to actually change the value of the reference that's being passed. And this is a good thing because clearly that's not the intention of the program. It wouldn't make sense for squaring a number to change the value of the number you're squaring. Can anyone see any other issues with this code here? There's a whole bunch of them. don't necessarily have to do any particular order.
Could you put 2 in the do stuff declaration? One in front of the step vector and one in front of the...
Are you talking about down here somewhere?
No, right in the middle. Line 10.
Oh, sorry, the do stuff function. Okay. Yep. And what was that?
If the vector and the int don't need to change, because you put one in front of the stud.
Oh, you mean, so put a const here and a const here?
Not the int in the...
Oh, this const? Or sorry?
Yeah.
Here?
Yeah.
You probably don't want to be attaching constness to the parameter that you're plugging into the template. I'm not even sure whether you can do that. For some containers, you can't. Like, it actually has to be an unconst qualified type. To be honest, I'm not sure, but it might not even be legal. But even if it is legal, you probably wouldn't want to do it. Like, the way that you'd want to say that this vector can't be changed is you would make the vector itself, like the reference, a reference to something that's const. So rather than putting the const here, I mean, the spirit of what you're trying to do, I think, accomplishes is noble. But rather than putting the const here, you want to put the const out front here. So it's a reference to a vector that's const. So you can't mutate the vector in any way, which would also include mutating any of the stuff that's inside the container, which are the ints. Any other thing that people can see is wrong? So we've got like 2. There should be a const up here. There should be a const in front of std vector. There's still probably like maybe 2 or 3. Yep.
If you put a const at the top, then I guess we have to put one on line 22 as well, where the 42 variable gets initialized.
Yeah, this would probably make a lot of sense, right? Because since we're calling the variable 42 and we're initializing at 42, it was probably the programmer's intent that the value of this variable shall remain 42 until the end of time. And if I try to change it, it's probably a coding error. So if you put a const in here, I mean, it won't make any difference really from the point of view of this example, but I would argue that it probably makes things more correct. And I think on the next slide, it actually does do this. I would argue it's more correct to put const here because it's fairly clear the programmer intent is that I never want to change this. And if this was part of a bigger program, like what that would save you is if you did make this const and then accidentally somewhere else in the code you did something that would change the value of 42, the problem gets caught at compile time because it will be actually be flagged as a compiler. And the basic principle of catching errors is the sooner you catch them, the better. So better to catch them, before they ship to the customer, find them first. But it's better, when you're doing the development, find the bug when you're compiling rather than when you're running the code. I think you're next.
If you put const on line 10 for the vector v, the reference to the vector
Yeah.
v, how does the compiler guarantee that the method call on 11 doesn't change the state of v? Like, would you not be allowed to make that method call?
I think things are maybe backwards in the logic that you're using to reason. So if we made this const, then what's happening is do stuff is making the promise that it won't change the vector that's being passed in by reference. So it's promising not to change v,
Right.
like because it's passed by reference. So really what it's doing is it's making a promise not to change this variable here that lives in the caller. But v is not, whether it's not even const to begin with. So like even if it didn't make the promise, it's kind of okay because we're allowed to change v in principle. It maybe wasn't the programmer's intent that they want to change v, but there's nothing here to really preclude it. Although maybe we want to add a const here because if our intention was not to change v, maybe we want to make it clear by putting a const in front of this declaration. But once we did this, if we made v const by adding a const out here, for example, then we have a problem without the const here. Because now when we try to call this function, this reference refers to something the compiler knows is constant, but we're not promising not to change it. So then that would cause an error. But I think what you're asking about is sort of flipped around the other way, which is not a problem, if I understood correctly. Yes, no? If you need time to think about it, I can come back to you. You can put your hand up again. Mm-hmm.
Should 11 be const int star const IP?
Const int star const. I guess you could have both of them const. I think the more critical one is the first const. Like you want to make this a pointer to something that's const. And actually, once we change this line here to make this const, then this will also have to be, I think this will also need to be const as well. Because you kind of get a domino effect. You're not allowed to change the vector, but if it gives you a pointer to an integer that you can use to change what it points to, now we have a backdoor that we can change the vector. So yeah, so actually we need a const here, and you were also suggesting to make the pointer const as well, which is okay, because I don't think we actually changed the value of IP anywhere. So you could maybe argue that you might want to make it const. I mean, sometimes it's less critical, like there's often a lot of places where you can make the actual objects themselves const. In some cases it makes sense, like for example, In the case of the 42 variable on line 22 at the bottom, it's pretty clear that probably the intent of the programmer is this should have the value 42 at the end of time. Whereas in this case, it's maybe kind of due to the cryptic variable name IP. It's like, well, what's that? It's a little bit less clear. But I think that probably what you're suggesting is a good idea to make both of them const, because you're certainly not intending to change the value of IP itself. So you might want to fix it so that it always points to v.data, what that is returned by that function.
When we're initializing vectors, is there any reason to put const on the actual template type as well? Does it do anything?
Yeah, I think you're asking maybe something related to comments I made before. So you're talking about, like, for example, adding a const in here, const qualifying the actual template parameter for the container.
Down in main, like, we're initializing an integer. Does it make any difference to say that we would have a constant that is like data members can't be modified?
So you're talking about, well, it's kind of the same stories up here. So you're saying, what if I plug in constant here?
Yeah, does that mean? To
be honest, I'd have to check. Like, basically, you're asking this question which relates to exactly the same line up above. It's the same issue, but I guess you weren't equating them. I honestly don't know. I'd have to check the standard to be sure, but I think it might be the case that the types that you're plugging in for the container, like the type of the elements in the container, like this thing here, it may be the case that it's not allowed to be const qualified. I'm not sure. I think it actually may be allowed to be const qualified, but it strips the const off internally. But I can't remember which is the case. But the bottom line is it probably won't do what you think it might not do what you think it does. And the usage, anyway, I'll just maybe leave it at that. Did that sort of answer your question? It's the same issue as here as well, because here we're also instantiating the vector template with int. So it's like an issue of whether we put a const int in here or an int and similar down here. But again, I have to check that to be sure. I think it might actually be valid. I think that internally it may kind of strip the const off. Mm-hmm.
Is there any chance of it printing out the value, trying to print out the value of the end of the iterator in that loop, or is that not?
The value at the end? Well, end is one past the end, so it doesn't refer to valid data. So if we were to dereference the, like when we're looping here, I think is what you're talking about. If we were to dereference I, like say star I when I is referring to end, this is undefined behavior. Like we don't want to do this because we don't, like, it doesn't refer to anything. But this won't happen because, like, the way we're looping here, we loop on as long as I is not equal to n. So as soon as it becomes equal to n, we get kicked out of the loop, and we won't do the body of the loop, which is going to dereference the I. So there's not a bug in that regard. But if we did dereference n, this is a problem. This is like a very serious problem, maybe even worse than the constants issues, because those will probably get caught at compile time. This will just cause really weird sort of behavior at runtime. Any other comments? Yep.
I had a question about line 11 when you're calling v.data.
Yep.
You mentioned the change that you would add const when it's actually passed in by reference for v. So then, are you guaranteed some like non-sleazy backdoor way to, when you call v.data, that it won't actually change v, since v is referring to something that's not const, but then when you're passing it by reference, you're changing it to const. So like, are you guaranteed somehow, will it check that when you call v.data, there's not some sleazy backdoor way within the data method that it won't actually change?
Well, the mechanism, if I'm understanding the question correctly, the mechanism, like, so v.data, I believe, is actually overloaded. There's a const and non-const version of the member function. And in this particular case, if we add const to vector here, like in the correct solution, then the type of v is like it's a reference to something that's const. So because this data member, I believe, is overloaded, or at least ultimately what's going to happen is it will invoke the data member, which is it will invoke the function member called data, which is operating on a constant object. So it will be implicitly making the promise that it won't change the vector v. So this is the reason why, like, if we change this to const, then we have to be careful to also change this to const, because then you kind of get a chain reaction. Once this is const, then this thing is going to be returning a pointer to a constant integer, but you can't assign a pointer to a constant integer to a pointer that's not constant, because then that would give you a backdoor way whereby you could change something that's const. So like often what you find is, like, if you're really having a bad time with const correctness and a lot of things are incorrect, it becomes very painful to fix things at the end, because what happens is you go, oh, there's one mistake here. You fix that, and now there's 23 more compile errors, because changing that causes a lot of other places where previously you didn't realize something was wrong to be exposed. So you get kind of this chain reaction. So I can't remember. I think the way the code's actually written here, it will actually compile, because although there's lots of bad stuff going on, I think none of the functions are invoked in a way that that it will cause the problem to manifest itself, where you're actually going to be passing constant objects in to functions that are passed by, where you're passing by reference, and then they're going to be trying to change something that's constant, like, because none of the things that are being passed in to do stuff, like we call it here, this is not a constant object. But for example, if in your code you realize, oh, I really wanted this to be a constant object here, then all of a sudden the whole house of cards comes tumbling down, because then you change this to a constant object. Then we would call do stuff, because this is not a reference to const. Then we could be changing a constant object if the compiler allows us to invoke this function. So then you get a compile error. And then maybe you go, okay, well, I changed this to const. Well, then once you change this to const, then this line doesn't compile, because then v.data is actually a pointer to a constant integer, and you can't assign a pointer to a constant integer to a non-constant integer. And it's just a big mess. So like the big advice I would make for const correctness is like, don't say, well, I don't really understand, I'll leave it to the end. It make things much more painful to try to fix things at the end. Do it correctly from the beginning.
So to clarify, is the data function in this case a constant member function? Like would in its definition somewhere, like would it have to be a constant member function? Like say you created data.
Well, it would be typically, I think it would be overloaded. So because you can have functions with the same name, but that they differ in their parameter types and so on. So basically you have there's an implicit parameter, which is basically although we don't write the v in the brackets here for the parameter list, in principle, v is a parameter. It's an implicit parameter to the member. It's the object that we're operating on. So v itself is either an object that's const or non-const. In this case, if we change this to be add const here, then v becomes a reference to a constant object. So then if v is constant, then when we invoke data, if data is overloaded and there's a const member function and a non-const member function, the one for operating on a constant object, one for operating on a non-constant object, that the overloading system prefers the one that matches in constant. So we'll invoke the const member function, but the const member function by definition is not allowed to change the object you're operating on. So like things will basically work because of the way that the particular container is implemented, or the particular API that the container uses. Any other questions? Yeah?
And does the constantness of v affect the data, the method that returns? Like if there is a method that returns a value that is
so you're talking about the data member function, like this guy here that's
yeah,
about?
so, yeah.
I mean, the value that's returned is not going to be different depending on whether it's constant or not. Well, unless making it constant or not somehow changes the layout in memory, so things are positioned differently. But at least I think for the example that's shown here, it would not be likely to make any difference. So the only difference is like what the only difference is what you are allowed to do with the value that's returned by data. Like in either case, it's going to be returning the same value, because the chunk of data that holds the actual underlying elements of the array it is where it is in memory. It doesn't really matter whether you're allowed to change it or not. It exists where it does. So the value doesn't change, but the type that's going to be returned here may be different depending on whether you put const in front of vector or not. You may be getting a pointer to something that's constant returned versus a pointer to something that's not constant being returned. And this will dictate what you can and can't do with the pointer. Like, because if you pointer to something that's constant, you can't dereference it and change the thing it refers to. Answer your question, or if not, maybe you can clarify. Any other questions? Okay. Well, let's move on then. I don't know. I think we caught all of the things here. I mean, the most important ones are the ones at the top here. Const here, const here, const here. Oh, we did miss one. This should be a const iterator, because all the iterator types for standard library containers, there's member types called iterator and const underscore iterator. The difference between them, the one that's const underscore iterator, this is an iterator that you're not allowed to change the thing it refers to. So when you say star I for the iterator, it's a no-no if you try to change what star I is, its value. But what we had in the previous code here, the original code, we just had iterator. So we're allowed to dereference this iterator and change what it refers to. If you look at what we're doing in the code, though, clearly the intention of the code here is not to somehow change the value that I is referring to. So arguably, this should be const underscore iterator. In fact, if we change this to const, again, we get kind of a domino effect. If we change this by adding a const here, then this has to become a pointer to a constant integer. And then also this has to be a const iterator here. Otherwise, we're saying when we iterate over the container, we might be changing the values. But no, the compiler say, no, you can't do that because you just said it was const, the parameter that's passed in. So this is what I mean. You often get this domino effect. One, if you don't try to make things const correct from the beginning, then when you realize, oh, this one thing is wrong, what you find out, that's just the tip of the iceberg. It makes like everything else wrong all over the place. And then you spend like a whole afternoon maybe trying to put const in all the right places. And if you were designing the code too, then you're into the problem that maybe your API is just fundamentally broken. Like your API is missing const in places where it should have them. And then if there's API changes, it's even more of a hassle to try to fix. Anyway, I better stop here for today. I can maybe answer your question like outside of the context of the